7.1. And again, I want to draw bar diagrams to get a sense of what's going on here, to see what we're actually looking at here. So the first thing that I would do here is that it says the figure shows an overhead view of 3 horizontal forces acting on a box that was initially at rest, but it now moves across a frictionless floor. Determine the net force done on the box by the 3 forces during the first 4 meters of displacement using 2 different ways. So the first way that I want to do is the ideas that what we've been talking about. And then later on, after I introduce the dot product, I'm going to come back and I'm going to do this piece right here. So for right now, I'm only going to focus on this first part just to give you some numbers so you can get a sense of what is going on. Now, the thing that's really important here is that the phrase that should really stick out for you is this guy right here. It says, determine the net work done on the box by the 3 forces during the first 4 meters of displacement. So the question is, what do they mean by the first 4 meters of displacement? And what you're seeing here is that there is no direction to the displacement. And so that should cause you some concern because you're thinking the displacement and the force have to be pointed in the same direction. However, what we do know here if we calculate F net, then the box must slide in the direction of the net force, which then means it tells me also the direction of the displacement. So let's go look at that. So the first thing that I'm going to do here is that I want to go calculate this. So what I'm going to do is that if I look at that box, I need to calculate the net work. And I know that the net work is then going to be the net force in the x direction times its displacement plus the net work in the y direction times its displacement. And the only way I can do that is that I have to break down this system into a free body diagram. So this implies here is that I must get the force components. So here I go. So what I'm going to do here is that I'm going to set up my block. So here, or my box. Here's my box. So what I'm going to do now is that I'm going to come in and I'm going to start drawing my forces here. Well, note that I have to use these coordinate systems. And so when I look at this thing here, you can see that the force F has 2 components. It's going to have an X and a Y component. Again, using the standard coordinate systems here, since this is a top view, I could see that the force F is going to be what? Well, I have a force in this direction. So then I'm going to break it into its components. So this guy is going to be F3X. And then this guy is going to be F3Y. And so in this case, we can clearly see that when I write down these force components, that the angle is measured relative to the horizontal axis. So I can write cosine of 35, and I can write f of 3y is then going to be f3 of sine of 35, where I then going to write the force F3, because it tells us, as 10 newtons. Okay, so I got the first two forces. Now, if I look at F1, you could see that F1 is pointed in this direction, and there's only an x component to F1. So I have to pick a direction. So how about if I pick directions like this here? So if I pick a direction like this here, I'm now going to say that F1 is then going to be in the negative direction here. So then I come over here and I'm going to say that F1 of x is then going to be minus F1. And according to this here, it's going to be 3 newtons, since it has no y component. So then I get to the blue here. And so when you're looking at the blue, note that the angle is measured relative to the y-axis. Okay, I'm seeing some chat here. What delta x and delta y means is the displacement. Okay, never mind, I got answered. Thank you for the help. And so then what I'm seeing here is that if I look at the blue vector, what I'm seeing here is that the blue vector, I'm going to change this angle so that that reads 40 degrees. So now I'm measuring it relative to the x-axis. So then that means here, I'm going to have a vertical component. It's going to be F2y, and I'm going to have a vertical x component, which will be F2x. So when I look at these guys here and I break them up, and remember, I'm using the angle of 40 degrees, not the angle of 50 degrees, then what I'm seeing here is that F2x is then going to be minus F of 2 of cosine of 40 degrees. And then I'm going to have F2y as F of 2 sine of 40 degrees. So then what I got to do here is that I could go in and I could calculate these numbers here. So here I go. So now I'm going to get the net force in the x and F net in the y. So F net x is then going to be the sum of 1x, sum of 2x, plus the sum of 3x. And if I do that, I'm going to punch in my numbers here. So here I go. F1, we already wrote that this is 3.00. Well, that's a couple of O's here. And then F2 is going to be minus F2. And 2, if I come up here and I look at this thing, 2 has a magnitude of 4. So then I'm going to write 4.00, and it's going to be cosine of 40. And then the x component for f of 3 here, f of 3 is 10 newtons times cosine of 35. So if I compute that number, I'm going to get that this number is minus 2.13 newtons. Then I'm going to do the exact same thing here. So I have 3 components. And so we already know that one of these is 0. For F1, we already know that that's 0. So I only have to focus on 2 and 3. And in 2 and 3, what I'm seeing here is that 2 is then going to be positive of 4.00 newtons. And this is going to be sine of 40. And then I'm going to get positive 10 times sine of 35. And so when I compute this number, I end up getting a value that reads 3.17 newtons. So now I have my components of the net force. So when I look at the components of the net force, what I'm seeing here is that picture-wise, where is this guy located at? Well, for starters here, I could see that it has an x component in the negative direction. So in other words, if I go in and I draw this guy, it tells me that I have an x component in this direction. And then I have a y component that's larger in the y direction, but it's in the positive direction. So if I sum these guys together here, you're seeing that I have what? That my net force is in the second quadrant.
Hey Carlos, why isn't F2 of y negative? Because isn't F2 of y in the negative direction according to the free body
Oh,
diagram?
let me see. I probably screwed up. Here, let me get my mouse here. 2 of y, did I make that positive?
It says,
I did.
Yeah.
It should be positive. I'm negative.
Oh, okay. Thanks.
I still think that that's the same answer. So I now have the net force. I could get the direction, right? I could come in here and I could measure this angle because I could get F net and F of x. So here's what I'm going to do now. So now what's the magnitude slash direction of F net? Well, I know that F net has a magnitude of F net x squared plus F net y squared square root. So if I calculate that number, it should be minus 2.13 squared plus 3.17 squared square root. So that should give me a magnitude of 3.82 newtons. Now, if I want the angle, I got to take the tan inverse of this guy, which should then be F net y, F net x. And if I compute this guy, putting in the same numbers, I'm going to get minus 56.1 degrees. So I now have the angle and the magnitude of this thing. So the question is, I know that when I look at this thing, the work done is only in the first 4 meters. So I know that the displacement must be in what direction? Must be in the direction of the net force because it's starting from rest. So from this here, we know the displacement is along the direction of F net, which then tells us here that then the net work in this case is then going to be the net force times the displacement in that direction. And I'll call it, maybe I shouldn't call it x, maybe I should just call it D here. And so in this case here, it's going to be 3.82 newtons times 4 meters, which then should give me 15.3 joules for the net force, or the network, excuse me. To just stress the idea, I want to go back to this example that we did last time. But this time, I want to do the work in terms of the dot product. And this is what we found last time here. What we found out is that when we calculated the work, so from part A, we calculated that the work was 15.3 joules in the direction of the displacement, right? That was the net work. So what I want to do here is that I want to recreate this thing. So I don't want to go back and do all the components and stuff like that. So I'm just going to steal from the previous example. So from part A last time, we determined the following thing here. Well, we determined that the force, that the net force, which would then be the sum of force 1, 2, and 3, we got two components. We got f of x, we got f of y of the net force, and this was equal to 2.13 in the I hat direction plus 3.17 in the j direction. Wow, I remember that being in the negative direction for some reason. I'm pretty sure it was. Okay, that's what that was. And then what we did here is that we were, this is in units of newtons, and then we looked at the displacement vector, and the displacement vector was what? I remember it being 4 meters, and it was in the negative 56.1 degree direction. So if I look at this thing here, it's not in the component form yet. So what we need here is that we need to get this into component form. So the displacement in component form, just to remind you here that we said that the displacement last time looked something like this. And then we had a vector like this here, where this angle was 56.1 degrees right there. So if I compute this, this is really then what? It's going to be 4 cosine of 56.1 and then 4 sine of 56.1. But then I have to pay attention to what? I have to pay attention to the quadrant. So we know that this is negative in that direction right there. So what I'm going to do then is that then I'm going to go do the work here. So if I now calculate the work, so now I got all of that. So now I'm going, so by the way, this should be dx and dy. So now here I go. So the network, so the network is then going to be the net force dotted with the displacement. So that means then I'm going to have what? I'm going to have minus 2.13 newtons dotted with the x component, right? So it should be something like this. Just to be clear, it's got to be the net force in the x direction times dx plus the net force in the y direction times dy. And so when I write this out, it's got to be minus 2.13 newtons times minus 4 cosine of 56.1 plus 3.17 newtons. By the way, this should be in meters, times 4 sine of 56.1 meters. And when you compute that number, what do we get? We get 15.3 joules for the net work. In other words, we're getting the work using two techniques, either the dot product or the other one.